All right, I guess that's it. Everybody, oh, just as I click the button, every time. All right, Wendy's here too. Good. So, good afternoon, everybody. And Alondra's here too. We actually have everybody. All right. Next time. All right. Okay, so today is going to be a super special, awesome day because we get to play with my favorite things, 3D shapes. Yeah, it's going to be awesome. Although we won't get into too much detail. This is still just our basic preview of everything, getting the vocabulary and the terms sorted, and then we'll get to do more in-depth analysis later in the quarter when we do area and volume. And then next semester, the whole fourth quarter is dedicated to three-dimensional geometry stuff. So that's going to be real fun. But before we do that, let's look back at yesterday's stuff with quadrilaterals and circles and make sure we are all on the same page there. So please take out your work from yesterday and compare it to my final answers here. Number 1, 2, 3, 5, and 6 should all pretty much be the same. Again, you might have had your letters swapped around a little bit. Make sure H is on one of the acute sides. Right? K has to be obtuse, and these have to be similar, so they kind of have to be in this order. But otherwise, those were mostly done. Number 6 talked about the perimeter, so you should have added lengths indicators on 2 of the sides. You only need to do one side. We know from the rectangle that the opposite will be the same. You don't need to label that one as well. So one side is A, one side is 2B. Which one was which didn't matter. But the trapezoid was probably where you ran into trouble. I did at first. I was like, ooh, wait. Maybe I set you guys up for failure there because I saw, hey, perpendicular, we better have a perpendicular in our trapezoid. But, the perpendicular does not end up on the trapezoid itself because you have to have T, R, A, and P as your vertices. And you have to have the TR parallel to AP, so you can't put TR here on one of the slanty sides. And you have to have P, E, and A be collinear. Well, A and P I know have to be my endpoints because it's part of the vertices of the trapezoid. So E must go somewhere in the middle, which means this segment RE is not part of the trapezoid itself. It's not one of my sides. RE is not a side of the trapezoid. It's some new segment drawn in to be perpendicular with PA, which means my trapezoid actually has to extend out and be this double slant guy here. Okay? This is why we started with the reasoning, so that you have the deductive skills to work through it. If I know it, this has to be true, then it follows it must be this way. All right? So you can work through problems like that. Now, the next bit was a little more straightforward, naming some of the polygons inside here. So our square, one option is ADFC. That's this square in here. It's the only square on the picture, but so you have to use those 4 letters, but what order you put them in didn't matter. You could go FCAD, you could go backwards, CFDA, okay? What order you put them in didn't matter. The parallelogram could be almost anywhere. I went with GIFD. That's this little guy here. Again, you could go backwards, you could go IFDG, whichever order. You could use this great big rectangle here. Any rectangle counts as a parallelogram. A square is also a parallelogram, so you could reuse that. You could use the JDEF. That's a parallelogram. And in fact, that is more specifically a rhombus, so that's what I used there. A square is also a rhombus, so you could have repeated your answer from square here under rhombus. So there's a couple options for rhombus there. And then the kite, there is one shape here with HDBF or HFDB, right, that is uniquely a kite and not any other shape. But it turns out rhombuses are also kites. So you could have repeated your rhombus answer, and a square is a rhombus is then also a kite, right? It doesn't break the definition. Kite is defined as two pairs of adjacent congruent sides. These two sides are congruent. These two sides adjacent and congruent. Look at the rhombus. Two sides adjacent and congruent. Two sides adjacent and congruent. Just because all four of them are congruent doesn't prevent you from treating them like two pairs, okay? So it's more specific, but it does fit our definition of a kite. So every rhombus is also a kite. Kind of handy. Okay, any questions from that page? Nope. All right. And did you guys want to log into the Zoom so you can actually see the visual here? Onwards to circles. So here are my answers for that. Number 1, we already knew that one, 48 degrees. Number 2, measure of arc PR. PR is over here. It is half of the circle minus that 48. So 180 minus 48 gives us 132. Number 3, PQR. Gives us this half of the circle plus 48. You must go from P through Q to R. They give us those 3 letters for a reason. So we get 228 there. And then number 4, 312 degrees. Q to P to R is almost, but not quite all the way around. We are this 48 bit short, so 360 minus 48 to get that. 5 and 6, basically unchanged. Right, I drew those in class, and that was all you had to do. And then number 7, the 3 other coordinates here. From the 2 points given, you could find the distance between them, just a simple subtraction, to get a radius of 5. And then you'll add on your radius to the y value to get 3, 7. Subtract it to get 3, negative 3. And add it to the x value to get your third point, 8, 2. Any questions on the circles page? No. All right, then let's move on to our intro to 3-dimensional shapes. So we're introduced to 4 main types of 3D shapes in this section: the prism, pyramid, cylinder, and cone. I have a sampling of them here. And I'm sure if I gave these to any one of you, you could probably start sorting them. And here's the prisms, and here's the pyramids, and you could probably figure that out pretty easily. But I'm going to go through and we're going to define what are actually the unique traits that set these shapes apart, okay? So that you can identify them in different formats and then practice drawing them. I'm going to show you some tricks in drawing 3D objects. It's almost like an art class here, right? So let's start with a visual representation. I'll zoom into the camera here. So here we've got the prisms. Here is a pentagonal prism right here. Can you guess why it's called a pentagonal prism? Versus here is another prism. This one is, though, a triangular prism, okay? Triangular prism, pentagonal prism. And then we go on to the pyramids, the nice pointy guys. Here's our classic Egyptian-style square-based pyramid. Versus here is a triangular pyramid, okay? So 2 different types of pyramids there. The cylinder, we see these all over the place. This is your can of soup, right? Your water bottle, a cylinder right here. And along with that comes the cone. You hold ice cream in it, or you put it on your head. At party time, hopefully those are not the same cones, but there is the cone shape. Probably fairly familiar with that. So the main difference here comes in the bases of the shape and then how the bases get connected. Okay? So we're going to make our chart here. We'll start with a prism. A prism is defined as a three-dimensional shape having two congruent and parallel polygon bases. And those two congruent polygons are connected to each other by a bunch of rectangles. So the sides of the prism are all rectangles. Here's my pentagonal prism again. Notice I've got one pentagon right here. Flip it around, there's another identical, perfectly congruent pentagon right there. They are parallel to each other, perfectly straight up and down across from each other. They're not slanted inwards one way or the other. Okay, they're the same size. If I made one of these smaller, I'd get some funky kind of cone, or towards a cone or funnel shape, and we don't want that. We want perfectly even. All right? It doesn't need to be a regular pentagon so long as both pentagons are exactly the same. And then between them, you have a whole bunch of rectangles connecting the two. All right? And that's what's going to make it very easy for us to draw. We literally just need to sketch up a pair of either pentagons or squares or triangles, whatever you like here. I can do either one. In fact, I've put together a quick little poll here. Let me paste that in there. So they're on the Zoom chat, and if you're watching at home on YouTube, you can go here as well. Vote which one would you like for me to draw. Would you like to see a triangle-based prism or a pentagonal-based prism? I would include square and even hexagon, but I did those in the other classes. Let's not repeat things. You can go back and watch the videos from those classes if you want to see one. All right, I've got 2 votes in. 3, 5, 7, all 4 pentagon. I figured pentagon would win. Of course you picked the most complicated one. All right. That's okay, because it's really not all that complicated. Here's what we're going to do. We're going to start with drawing one of our bases. Draw a pentagon. And doesn't have to be a regular pentagon. In fact, I'm going to purposely make this side a little bit wide there. Okay, a non-regular pentagon. So you know it doesn't have to be as such. But don't make it too crazy, because you need to now draw the exact same thing again, but this time shift it over a little bit up and to the right. So I'm going to draw a similar pentagon, except not only similar, as congruent as I can possibly make it over here. And I'm only going to be using my straight line tool. That's going to be a curve, isn't it? Yeah. Why does that not seem quite right? That's not bad. Okay, that would be why. Here we go. I'm going to try to improve this on the fly a little bit here. Make that a little bit higher and then connect. That looks better. Okay. And then you put these as close to each other as you want. If you put them real close to each other, you'll have a short prism. You could even have them overlapping. Okay? If you put them farther apart, you'll get a longer prism. But now all we have to do is, wherever they end up, connect each of the corresponding vertices with a straight line. Oh, look at that, it's coming together. So just kind of pop into the visual field there. I'm like, oh yeah, it's now a 3D shape. I can see it now. Your brain will fill it in for you. It's a really neat effect. And if you want to improve upon that effect, what we can do is make sure our brain understands which lines are in front and which are supposed to be behind, because if you were to look at an actual prism, you can't see all the lines at once, especially if it was completely solid, right? The lines in the back, all right, would be obscured from your view a little bit. So we're going to mimic that by making these back ones into dashed lines. I'm just going to go through with my eraser and turn those into dotted lines. See, I wouldn't be able to see that one. I wouldn't be able to see that one very well. This one's tough because it's really close to the other one. But we'll turn that into a dashed line there. And then all of this becomes a dashed line as well. All right, so any of those back faces that you couldn't see immediately, that way your brain isn't flipping to, is it popping out of the page or is it going into the page? It's very clear what's in the foreground and what's in the background. And that is the basics of 3D art. All right? There you have it. This needs an S, 2 polygons. Okay, the pyramid then. The definition of a pyramid is to have one polygon base and sides all made out of triangles that meet at the vertex. So drawing them is pretty similar, except this time, instead of 2 bases, we only draw 1. And instead of drawing the base head-on, facing you directly, we want to draw our pyramid usually. I mean, you could still draw it like this and connect it as such, or might get drawing like pointing out towards you, maybe a little bit of shading there. But I want to draw it looking like it's sitting on the desk and I'm looking down forward at it, right? This kind of angle. So my square here does not look like, from your view, like a perfect square. It doesn't fill the screen the same way a perfect square does, like that kind of view. So I need to draw it a little bit slanted. Right? So a square would be more like a rhombus sort of shape, except I'm going to go, let's try a pentagon, since we started with the pentagon. If I did the same base as I used there, I'd have that guy, this one would go up a little bit like that, this one would be over here, but squashed a little more, this one would be squished to the side, and straight line, please. All right, so you get kind of a squashed looking pentagon there. And I think I'm going to change one more thing about it. Let's make this kicked out at an angle. I like that. All right, and then we pick a point above our pyramid. You can make it down low if you want a short, shallow pyramid, way up high if you want a tall, pointy pyramid. I'm going to go somewhere in the middle, make a point above it, and connect that point to all of the vertices of your pyramid. One there, one right there, one there, one there, and one there. Okay? One of them gets almost covered up by the other. That's okay. We use our same effect here. We make these back lines into dotted lines. So we know that those are not immediately visible to us. And we get our pyramid shape. And all of the triangles meet up at that tippy top point and that is the vertex. All of the corners on a three-dimensional shape, every point where the faces and the edges all meet, that is called a vertex, just like in the polygon. The corners are called vertices, singular vertex, but the pyramid, one of them stands out. It is unique among the rest of the vertices because it doesn't touch the base. It's all triangles. So it gets the special name of being the vertex. It's the important one, you see. So there's my pyramid there. All right, next up, we've got the cylinder. And the cylinder is our soup can, right? And it's very much related to a prism. You can see there's a lot of similarities. We've got the two flat parallel bases and then connected with some semblance of a side. This is where sides is in quotes here. So a cylinder, the difference is instead of polygons, it uses circles. Two congruent parallel circles. And the side is actually one rectangle. Wait a minute, Mr. Apple, but the side, it's round. How can that possibly be a rectangle? Well, if you were to cut this guy open and unfold that side, roll it out, you would get a rectangle. Imagine peeling the label off of your soup can, right? That's a rectangular sheet of paper, isn't it? So it's one rectangle curled around the cylinder to make that single sidewall. All right, drawing the cylinder, pretty easy. I'm going to make some room here. Scoot up. Out of the way, pyramid. Drawing the cylinder is pretty easy. You could do it exactly the same way we did the prism. You could draw two circles and connect them with two lines. Done. I'm going to go something a little bit different. I'm going to use that technique for the pyramid base. I'm going to make the base at a slight slant and really go for that 3D effect. Okay, so it's looking down at a soup can sitting there on the counter. And when you look at it at an angle, you don't see a perfect circle there, right? This view is a perfect circle. This view, suddenly, it's not. It's slanted. It's more of an ellipse. So we're going to start with drawing that top there. Some sort of an ellipse. There we go. I'm happy with that. And then I would draw two sides straight down. How long do you want to make it? Are you drawing a tuna can, right? Soup can, tennis ball can, or Pringles tube, right? However tall you want to make your cylinder, and a matching one on the other side. And now we need a matching ellipse down here. So go a little bit above, wrap around, a little bit below. I went too far out that side. Just to the edge and back. Oh, come on. There we go. Good enough. All right? And then once again, if we're viewing from the top, we get to see the whole top side, but the bottom back edge would be obscured from us. So we'll make this into a dashed line. And now we have our nice cylinder. Yeah. Not too shabby. All right, so even if you're not a great artist, you should be able to use these basic techniques to at least convey what the shape is supposed to be. Now, cone is probably the simplest yet. We just have, like the pyramid, a single base, but like the cylinder, it is a base of a circle. Except the sides get more complicated. It turns out, if you were to take your cone, imagine you buy the party hats, and you cut one open and unfold it, or unbend it, and flatten it out, you would end up with a shape that is properly known as a sector. You might recognize it as a very wide slice of pizza, okay? If I had my base of my cone there, the side of it would look something like this, okay? A nice wide section of pizza. So it's not quite a triangle because it's got a curvature there. It's part of a much larger circle here. And it's going to be wider than you expect. If you expect your cone to be this wide, your sector is going to end up, a little over 3 times that width there because you're unraveling all of it together. It's going to be much wider, and that shape there, just in here, is called a sector. It's a slice of a circle. All right, and drawing the the cone, very similar to pyramid, except we start with a circular base. Add a slant, so a little ellipse there. Pick a point centered above it. Connect that point to both sides. There we have it. And for that 3D effect, go ahead and turn that back edge into a dashed line. There they are. Questions at this point? All right, your questions for today are fairly straightforward, but they're going to test your spatial reasoning abilities here. The ability to manipulate images and pick it up and imagine you had a physical thing and turn it around in your mind to be able to look around and see and understand it. The first 2 are just drawing, right? Use what we just went over and draw those 2 shapes. But the second set, 3 and 4, have to do with this new word net. What is the net of a solid? The net of a solid is what happens if you take that solid and like peeling the label off of our soup can. If you were to unfold the entire thing into a flat sheet of paper, what would you be left with? Or go the opposite way. If you were to cut out this shape out of paper and then fold along all the lines, they would fold along and combine into, and what would you get as a result? You can work through this very visually. If you're a strong visual spatial person, you might be able to work that out by manipulating it in your mind. And I'll give you an animation of that. If you just look up geometry nets on Google, you can get all kinds of really cool pictures of, ooh, look at that. Did you see it move? There's one in action. Let's see, there was a really good one of a cube that I came across here earlier. Where did it go? If I just press forward, does it take me there? I don't see the cube one, but here is a shape, right, doing that thing. So we take the flat piece of paper, we cut that out, and we fold it all up, and we end up with this new 3-dimensional shape, right? In this case, it's an octahedron. You can do the same thing for cubes and prisms, and there's all kinds of great images out there. Can't seem to see the one I saw the other day. I'll post a link on Classroom here of some really good interactive ones that you can actually, like here is one. If I go there, you can manipulate it yourself and see the evidence. Yeah, this is the site. Give it a second to load in here. And watch this thing in action as I drag the slider. It goes up and folds into the cube, just like that. And then I can pause halfway through, and we can pick this up and move it around. So if you're not seeing it in your head, maybe you can see it a little better now, what that looks like as it closes up and unfolds. And there's actually multiple patterns to it. There's different arrangements for the cube that you can even make this funny shape. This will still work as each side eventually comes in to make our box. Okay? That's a net. Now, if you have trouble with the visualization, maybe that's not your forte. We're going to keep practicing with it. It is a skill you can develop. But as far as identifying the net, you can just use these identifiers here to narrow down what shape it has to be. Because if there's a circle on the net, it's got to be a cylinder or a cone. If there's no circle, it's not a cylinder or a cone, right? They need circles. And then you can look to determine if it's a prism or a pyramid. Are there two congruent polygons that are not rectangles? Or is there only one standout polygon surrounded by a bunch of triangles, right? That would be the difference between those nets. So you can still work out what nets, what shapes these would have to be just from that, and then use our drawing techniques to sketch it up. All right, next up, you're going to have slices, cross sections. What happens if I cut my cylinder in half? What shape do I end up with? Imagine if I had a solid cylinder, right? You probably do this at breakfast all the time, right? You take your orange in the morning, you cut it in half, or your grapefruit or whatever. It started out as a three-dimensional sphere, and then you sliced it, and what's the shape you look at? That flat surface now is a circle, right? Well, what happens if I cut a cylinder this way? What shape do I get? Is it still a circle? What? That's correct. More generally, yeah, this one would be a rectangle. Very good. Right, so you're going to have to visualize that. If you want to get out some clay and actually play with it and make it happen, that'd be even better. And then 7 and 8 are the tricksy ones. Okay, this is really going to test your thinking skills here. Number 7 gives you a prism, a rectangular prism made out of smaller cubes. It really looks like a Rubik's Cube, doesn't it? I mean, it's gotten like an extra layer to it. It's a little bit too big. But otherwise, it's like a Rubik's Cube. So if you have a Rubik's Cube at home, pick that up, manipulate it around. Because what you're trying to do is understand that you can only see 3 sides of it at one time. And then they're asking you what is left behind on the unseen sides, the back of it. So if I hold this cube right here, you can see these front 3 sides. The 3 with my fingers on them are obscured from your view. If this was a solid cube, you couldn't see them at all. So they want to know how many of the smaller cubes are hiding back there that you can't see. And on the inside, maybe there's some in the very center, right? The cream filling in the middle. Well, you've got to be careful here, because you can't just count the squares. It says how many cubes. If you can see that top edge there, those squares along there are connected to the squares back here that you can't see. Those are the same cube, so don't accidentally count squares you can't see if they're attached to squares that you can, because they're part of that same little cube. All right? This is where the Rubik's Cube really comes in handy. Find one, get one, go to the Dollar Tree and pick up the cheap knockoff version for $1, all right? And play with it, visualize that, and practice with that. And if you can understand what's happening there, oh, these cubes are here, and that one's, put your finger on it, move it around, and say, oh, that's the same one there, all right? And then expand that into the 3 by 4 here. No, 3 by 4 by 4. Anyways. And then finally, number 8. Find the lengths of x and y, given this shape with the funny bump out on it. This is a 3-dimensional shape. It is a cube with an extra little rectangular piece extruding from it. You've got to recognize that as a 3D solid object, the height is the same no matter which side I measure on. If I measure on the right-hand side or if I measure on the left-hand side, the height is still the same. So when it says this side here is 4, that means anywhere from the bottom to the top is 4. This side over here must also be 4. From the bottom to the top is still 4. this on the front, from the top corner to the bottom edge, would still be 4. So use that knowledge, add and subtract as necessary to figure out what x and y are going to have to be based on the measurements given. You will need to use all 4 of those numbers. And that is more than enough hints that I can give you. Okay, any remaining questions? All right, seeing none, then I leave you the final 10 minutes of class to work.